Now we start the next session on integral equations. So we have already seen the transformation of a differential equation with initial conditions into an integral equation. So suppose the differential equation is given by y double dash plus a of x into y dash plus b of x into y is equal to g of x. With the initial conditions y of a equal to y0 and y dash of a is equal to y0 dash. We have seen that the corresponding integral equation is given by y of x is equal to f of x plus integral a to x k of x t into y of t dt. And where f of x and k of x t can be determined from these equations. This f of x and k of x t depends on a of x, b of x, g of x and also the initial conditions. A of x is the coefficient of y dash in the equation and b of x is the coefficient of y and g of x is the term independent of y. Now we also have seen a linear oscillator with initial conditions. So the equation is y double dash plus omega square y equal to 0. With the initial conditions y of 0 equal to 0 and y dash of 0 equal to 1. And we have already converted this differential equation into an integral equation, which is equal to y of x is equal to x plus omega square into integral 0 to x t minus x into y of t dt, which is a non-homogeneous Volterra integral equation of second kind. So now we discuss the differential equation of the linear oscillator with boundary conditions rather than initial conditions. Here we consider the linear oscillator equation, the same equation y double dash plus omega square y equal to 0 with boundary conditions y of 0 equal to 0 and y of b equal to 0. Here the value of the function at the initial point and the final point are given. So the value of the function at the boundaries are given. In the previous case, the value of the function at the initial point and its derivative at the initial point is given in the case of initial conditions. But here the value of the function at the initial point and the final point are given. So now rearranging this equation, we will get y double dash is equal to minus omega square y. So now doing the same procedure that we have done before, integrating this function from the initial point 0 to the arbitrary point x, we will get integral 0 to x y double dash dt is equal to minus omega square integral 0 to x y dt. So we know that the integral of this function is y dash, and so integrating it from 0 to x y dash of x minus y dash of 0 and rearranging the term towards right, y dash of 0 towards right, we will get y dash of x is equal to minus omega square 0 to x y dt plus y dash of 0. But in this case, in this boundary condition, y dash of 0 is not given. So we integrate again, we will get y of x is equal to y of x minus y of 0 is equal to minus omega square into integral 0 to x du integral 0 to x y dt plus integral 0 to x y dash of 0 dt. We know that in the boundary condition y dash of 0 is given as 0. So substituting it over here, and we know that this can be simplified using the identity. When the double integral occurs from 0 to x du and 0 to x y dt occurs, this will be equal to integral 0 to x minus t into y of t dt. So substituting that value, we will get y of x is equal to minus omega square into integral 0 to x minus t y of t dt plus integrating this is a constant and can be taken out, and integral 0 to x dt is x and y0 dash into x. So now we have to determine y dash of 0. So for that we impose the boundary condition in the equation number 1. So we will we know that y of b equal to 0. So put x is equal to b over here. Then we will get 0 is equal to. So instead of x we will have to write b minus omega square integral 0 to b minus t y of t dt plus b into y dash of 0. So in the equation number 1 we replace x with b. We will get this equation, and rearranging this, so from this we will get rearranging this, we will get b into y dash of 0, and therefore y dash of 0 is equal to omega square divided by b integral 0 to b minus t y of t dt. Substituting this equation in the equation number 1, so substituting the value of y dash of 0 over here, we will get y of x is equal to minus omega square into integral 0 to x minus t y of t dt plus x is already there, so we put x over here, omega square by b integral 0 to b minus t y of t dt. So this is that equation. So in order to simplify this equation, we break the interval 0 to b into 2, 0 to x and x to b. 0 is the initial point and b is the final point. X is some intermediate point where we are calculating the function. So the second integral is broken into two parts. So we can write y of x is equal to minus omega square integral 0 to x minus t y of t dt plus omega square x by b integral 0 to x b minus t y of t dt from 0 to x, and the other one from x to b. Omega square x by b, x to b minus t y of t dt. So this integral is broken into two parts, 0 to x and x to b. So now we can see that the first integral and second integral are from 0 to x. So we can combine this together and we can write y of x is equal to omega square into integral 0 to x x by b minus t minus minus is there x minus t y of t dt. Y is a common factor in this two integrals, so taking y as a common factor, and we will get like this, and we will write the third term as such, plus omega square x by b integral x to b minus t y of t dt. But we can simplify this equation as x by b minus t minus x minus t just by multiplying. We will cancel x minus t by b, t by b x minus t can be simplified as t by b minus x. And substituting it over here, we will get y of x is equal to omega square into integral 0 to x t by b minus x y of t dt plus omega square x by b integral x to b minus t y of t dt. This term has got no change. So now we define the kernel as k of xt is equal to t by b into b minus x when t is less than x, and k of xt is equal to x by b into b minus t when t is greater than x. So x is the intermediate point, the initial point is 0 and the final point is b. So when the variable t, so we draw a graph between t and k of xt. When t is less than x, k of xt has one form, t by b into b minus x, and when t is greater than x, k of xt has another form, and substituting those values in this integral. So y of x is equal to omega square into integral 0 to x t by b minus x y of t dt, where here the integral is from 0 to x. So when t is less than x means the value of t is from 0 to x. So in this case, in this region, so in this region we know that t by b into b minus x is nothing but k of xt. And the second integral is omega square x by b, integral x to b minus t y of t dt. We can take x by b inside. It's a constant with respect to t. It does not affect this integral, and therefore this integral starts from x to, in the region from x to b. That means t is greater than x. The value of k of xt is x by b into b minus t, x by b into b minus t. So we will get y of x is equal to omega square into integral 0 to x. In this region, this is k of xt into y of t dt plus omega square. X by b is taken inside the integral 0 to integral x to b k of xt y of t dt. So in this region x to b, this x by b into b minus t is k of xt. So now we can combine this together, 0 to x k of xt y of t dt and x to b k of xt y of t dt as a single integral. Y of x is equal to omega square integral 0 to b k of xt y of t dt. This is a homogeneous Fredholm integral equation of second kind. So now this is the kernel for this case, and we can see that the kernel is symmetric. K of xt is equal to k of tx. So when we change x and t, the kernel will not change. For example, when we interchange x and t, this will be k of tx is equal to x by b minus t, x less than t. So we will get this case. Similarly, this will be equal to t by b minus x, x greater than t. So we will get this case. So we can say that the kernel is symmetric. It is continuous also. That means this left hand limit is equal to the right hand limit. T by b minus x at t equal to x is t by b into x by b into b minus x is equal to x by b minus t at t equal to x. So putting t equal to x, we will get x by b into b minus x. So these are equal. So we can also see from the graph that the kernel is continuous, and the derivative of the kernel with respect to t is discontinuous. So if we take the derivative of this and the derivative of this, and if we take the difference between the derivative of the right hand limit and left hand limit, we can see that there is a difference of -1. So the slopes of this function, derivative means the slopes of k of xt are discontinuous. It is shown in figure also. So dou k xt by dou t is discontinuous. So these are the properties of the green function. So we can identify that the kernel here is a green function. So summarizing, if you are given a linear oscillator with initial conditions, the corresponding integral equation is a Volterra integral equation. And if you have given a linear oscillator with boundary condition, the corresponding integral equation is a homogeneous Fredholm integral equation with Green's function as the kernel. So, in the transformation of a linear second order ordinary differential equation into integral equation, the initial condition play an important role. If initial or boundary conditions play an important role. If you have initial conditions, the corresponding integral equation is a Volterra integral equation. If you have boundary conditions, the corresponding integral equation is a Fredholm integral equations. Initial conditions means the conditions at one end of the interval. Boundary conditions means conditions at both end of the interval. So the reverse transformation is not always possible. That is, integral equation to differential equation transformation is not always possible. There are integral equations for which no corresponding differential equation is known. So these are the assignments for you.